Now let's try a triple integral in cylindrical coordinates. So here we want to calculate the integral of z on the region that is bounded by the surface z equals x squared plus y squared and z equals 1. Now we remarked last time that z equals x squared plus y squared. Remember, that's just this paraboloid here at the origin. And we're capping it off in this case at z equals 1. And so our solid consists of this kind of solid bowl with a lid. Now when you're setting up a triple integral, typically we set up the z-bounds first. And in this case, it should be clear from the picture that z is between x squared plus y squared and z equals 1. And then you look at the shadow in the xy plane. And the shadow is sort of the widest part of this surface, and in this case that's the circle up here at the top. Well, that circle at the top is the intersection of z equals 1 with z equals x squared plus y squared. So in fact, we get the disk, which has as its boundary x squared plus y squared equal to 1. And you see that what happens is we get a shadow that we would want to set up using polar coordinates, because it's a full disk. And similarly, if we had, say, a portion of a disk, we might want to use polar coordinates for the shadow. And so that is what tempts us to use cylindrical coordinates for the entire integral. So let's go ahead and do that. So in cylindrical coordinates, z stays z, but x and y get rewritten in terms of r and theta. And well, from the shadow we see that r is between 0 and 1, and that theta is the full range between 0 and 2 pi. Well, there's only one other change we should make, which is that the lower bound for z we called x squared plus y squared, but in cylindrical coordinates that's just r squared. So we're going to integrate with respect to z and then r and then theta. Z goes from r squared to 1, r from 0 to 1, and theta from 0 to 2 pi. And also, you're going to get an extra factor of r. Again, this is just because when you're integrating using polar coordinates, you get an extra factor of r, and so that same factor shows up for cylindrical integrals. So if we do the inside integral here, the integral of zr dz is 1/2 of z squared r, and that's from z equals r squared to z equals 1. So that becomes 1/2 of r minus 1/2 of, well, r squared squared is r to the 4th, and combined with that other r is r to the 5th. Next, we do the integral from 0 to 1 of 1/2 r minus 1/2 r to the 5th dr. So that's 1/4 of r squared minus 1/12 of r to the 6th from 0 to 1. And that's going to be 1/4 minus 1/12 minus 0 minus 0. So that's 1/6. And finally, we have the integral from 0 to 2 pi of 1/6 d theta. And that's just 1/6 of theta from 0 to 2 pi. So 2 pi over 6, or in other words, pi over 3.